start there.
Thanks for coming, everyone. So our speaker today doesn't need much of an introduction to this audience. It is Zahra. She is into her final year of PhD and talking today on modelling ordinal first return maps in conjunction with our new favourite topic, minimum description length. Take it away, Zahra.
Okay, I hope everyone enjoyed this morning's talk. Is it? Sure. Is that better? Okay. Okay. Yeah. Our work here is I want to model the ordinal first return maps that I have, that I think probably all of you were in my talk last year, that what are them, and using the radial basis function and minimum description lengths for modeling this stuff. That's it. Just a brief introduction on everything that Michael said as well, that, okay, when I want to model a data set that I have, it's better we make an agreement from the sender and the receiver which kind of model class do we want to use for it. So at first for the first level I have to choose the model class that I want to use, and then after it I have to make the optimization for the parameter of the model that I want to set to model my time series. Here is the schematic diagram. I have an input, the input vector, which can be in any dimension. I have a hidden layer, which is my basis function here, and I have the output layer, which gives me my prediction from what is the next value. And the whole point that we are speaking about is the hidden layer here, that we are setting the radial basis function to each of these nodes, and we can use any number of them to make our model, and the minimum description length is coming to say us, okay, how many of these nodes do I need in my hidden layer to make the best model somehow, to have the minimum description length in terms of the length of the model and the minimum error that I get in my output. And that's it. So the way that I describe it is that, okay, I have the input layer, which is my time series, the data that I have, which can be in any dimension. I feed it to the hidden layer to make the model to get the output. What I'm doing here is that, okay, h of t is the vector consisting all the t from 1 to t. The x, i's are the value, and h is the vector. I'm feeding them to the hidden layer that I have at the middle, which I've put at s, the number of the nodes that I have in my hidden layer, and I can assign a weight for each of them to get my output. Just the brief review of something that Michael said this morning. And for here, in the middle, I can assign any nonlinear function to these nodes, but here I'm using the radial basis function, and for doing that, I'm randomly choosing between the Gaussian and top hat function, which the Gaussian helps me for capturing the smooth variation of the signal, and top hat helping me to capture the sharp variations. Or I can use any other one, which is sigmoid, wavelet, or anything else, but here I just use Gaussian and top hat. Yeah. Here it is. After that, I also can add a constant term as a bias if I need for my data, and also some linear terms, which I get any component of the input, assign a weight to them, and also add this to the output. So I'm just expanding my model by the bias, the linear terms, and all the things that I have in my radio basis function, the nonlinear terms that I had at the middle. And the linear terms, it should be, it's designed based on the embedding lag of my data. So all the L1 to LD, how many number of them that I'm going to use should be between the 1 and the lag of the data, the embedding lag of the data that I use. So here it is. It's the minimum description length, which first put forth by Rössler, and it minimizes the overall description length of the model and the data or the error. And I'm just trying to optimize the place that I have the description length is the lowest one in terms of adding these two components together. That's it. Okay, that was a brief review on what Michael's expanded this morning. And now the data that I want to model, my data is the first return maps. I have a dynamical system. I put the Poincaré section on it, which is a surface transversal to the flow of the system to get the Poincaré map of the system. Why do I do this? It gives me discrete time series instead of the continuous one, which is computationally more efficient, and it's one dimension smaller than the dimension of the original dynamical system that I have. And also it's helpful. The data can represent the dynamical properties of the system, which is efficient. Just as a brief review as well, how do I do this? This is, for example, the Lorenz time series, the Lorenz attractor. These are x dot equal to 0 surfaces. I put them transversal to the flow. I detect the intersections of the flow and these surfaces. And I'm just capturing xi minus y, xi plus 1, all the points that it's going through this surface. And if I plot xi versus xi plus 1, I can get the first return map of the Lorenz, which tells me about the properties of the Lorenz attractor in lower dimension, discrete, and nice. Okay, now how do I create my first return map? Okay, the first return map is a Poincaré section. I get it by putting a Poincaré section on the flow. So where do I put this transversal flow, these transversal surfaces on my flow? Finding the suitable locations for these surfaces can be challenging. The thing that I'm using is using the ordinal partitioning, which, okay, I'm coding the time series that I have. Instead of looking at the value of each point, I'm just looking at the orders of the point, and I code the ordering, which, okay, this one is increasing, this one is decreasing, this is up and down on any of them. And okay, I can use any kind of coding which is based on the amplitude or chronological index ranking, whatever it is. I use the second one here, but doesn't matter at all. It's just the coding that I put instead of using the amplitude of each point. Just as an example, this is the logistic map time series. I put a window, I'm looking at the amplitude of each point, just ordering them. I can have a gap between the points that I'm looking at their amplitudes. Okay, here I've chosen 3 points in my window, just because I like to do that. I assumed 1 point gap between them, which the distance between the points are 2. And I also can assume some overlap between the window. As long as I'm moving the window through my time series, I can assume an overlap and just continue doing that by the end of my time series. And these are the parameters that I'm adjusting based on the question that I have. And of course, as much as I increase the ordinal dimension, I increase the computational cost of getting my, for coding the time series, because the coding that I'm get at the end is, the length of the code is equals to m. So if I assume larger m, I increase the computational cost that I have, and the term tau and w are the terms that I can use them to adjust how much of the time series, how long do I want my window be, and how do I want to move it through the time series. Then at the end, I have something like this, that from the ordinal code of 312, I go to 132 and so on, which instead of using this time series at all, I can just look at this code. So I have a complete discrete values of, I can have a discrete values and just go through them for coding the time series. Okay, now the story up to now is that I have a set of points, which is the first return map points that I have. I want to make a model from them, and then use my model to predict these points, first return maps. So just assume that I have something like this in any dimension. I don't care. I have a set of points which are my reference point. In any dimension, I made a model based on them, and I did a prediction. So I have a new set of points in the same dimension on top of them. How can I want to say that? How can I quantify how much my prediction was good or not? What is my measure to compare these two set of points? Here is that, okay, I use two different measures here. The first one, I can grid the whole surface that I have my reference and prediction points, and look at the density of each of them in each cell. Like here, if I look at these only the red points, I have 2 points here, 1 point here, 2 points here, blah, blah, blah. I don't have anything in these cells, empty cells, and so on. So if I put the density of them, it will be something like this. I just use the color map to show the increase of the density, and I can do the same for the prediction set as well. I put the density of them on one histogram, the density of these prediction on the other one, and if I calculate the difference between these two densities, I can assume that, okay, if my prediction was perfect, if these two sets were exactly the same, this difference should be 0 in all the cells that I had. But here, my prediction is not great, so I have some, and also I use the same color map, which this cell is red, means that the density in this upper right cell is more than the blue one. The red one is more than the blue, but here, the blue here is more than red. And I can assign this one. But the other way that I use is that, okay, I can measure a distance between the points of these two sets. So what can I do is that I'm choosing the first point in my reference set. If the there is two things. First, the number of the points in my reference set and my prediction set are not necessarily equal. They can be a difference between the number of points that I have, and also the data can be noisy. So if I want to just capture the distance of each point with the closest nearest point, that's not the thing that can help me here, because the number of points are not equal, and it captures the noise as well. So I'm using higher number of nearest neighbors. Here I use 5. I assume the first point of the reference set. I'm looking at the 5 nearest point to it in the prediction set, and I'm measuring the radius of the circles that contain all these nearest neighbor points. Look at the second point, do the same, measuring the radius of the circle. And I can do it by the end. All the points of the reference set, and look at the radius of the nearest neighbor. I can do it vice versa as well, looking at each point of my prediction set and the neighbors in the reference set, and just recording all the radius of these circles. So at the end, the distance that I define between these two sets is average of the radius of all the circles that I have from the distance from my reference set to my prediction set is the average of all the radius of these circles, but because this radius of the circles is dependent on the density of the points that I have in my references, I'm just scaling by this average of the radius of the circles from the reference set to itself. Because if I want to compare two exactly similar sets, this d value that this average of the radius for the circles is not 0, because I'm looking at all the nearest neighbors. If I have two exactly similar sets, the point in a set has a large value for the circles which contains all the nearest neighbors. So I'm scaling this one with the average of the radius of a set and itself, and define this scaled value as my distance between the reference set and my prediction set. And the only difference from this one is that, okay, I'm putting the reference to the prediction on top, and here for the distance from prediction to reference, I'm using it vice versa, the blue circles that I have in previous slide. That's it. That's all the models that I want to use. Just I have a set of points which are the first return maps. I'm making a model out of them with radio basis function 1. I'm optimizing the model with minimum description lengths. I make a prediction, and then I use these comparison measures that I defined for comparing to define how much my prediction was good or not. Okay, here is the Lorenz system. You know, all know the equation and the attractor. Here I apply the ordinal partitioning on it with the ordinal dimension of m equal to 4, and assuming lag 6 and maximum overlapping of the window, and I assign the code of each ordinal window to the first point of the window. I get a code for the whole window, but I assign it to the first point, and I assign a color to each point, to each ordinal code that I have. So I can get a beautiful colorful time series like this. And if I zoom in, I can see that, okay, for example, here is the decreasing ordinal partition, which is 4, 3, 2, 1. And here is the point that I enter to this section, and up to here, I'm just staying in it to get to the yellow ordinal section, whatever it is. And yeah, here it is. From each of these ordinal coding, I can create a time series now. Just putting all these light green points together, take it out from the Lorenz time series and just put all the light green points together and so on. I can get a time series for each ordinal code. And if I put them on the embedded attractor, I can see that, okay, they give me nice sections on the attractor, which probably I can use them in order of the Poincaré sections and get my first return maps out of them. So I have a bunch of first return maps from different ordinal sections that I have, which I make them in this way. So here it is. Here I just changed the way of ordinal coding. Instead of assigning the ordinal code to the first point of the window, here I assigned it to the last point of the window. In theory, it doesn't mean anything. Nothing actually changed, just the location of the section has shifted a bit through the attractor. On the left side, I have this nicely clean attractor, which I use the high sampling rate for making my time series. On the right side, this is a bit noisy around here, which I just take the lower sampling rate for creating the time series. That's the difference. And if you look at the time series, I mean, both of them really looks like the Lorenz. It's just a bit, it's not as smooth as this one anymore. And I want to see how much this affects my coding, because if you look at these black points here, the area that they occupied is much wider compared to the high resolution one. And that's the effect of downsampling that I did. It's just changing the location of the points that are inter to each ordinal section. And that's it. Yeah, here it is. Here is the first return map of the same ordinal section on the high sampling and low sampling rate attractor, which clearly the high sampling rate one is much tinier and more clean compared to the low sampling rate one. But I'm going to use the first return map of the low sampling rate as a data to model and predict, because it's more realistic. In real data, I don't have access to the high sampling rate, and my data can be noisy, so it's more realistic to look at the blue one rather than the orange one. So here is what I'm going to do, is that, okay, I have high sampling data, I put the ordinal partitioning on it, I get the high sampling first return maps out of it, or I can get the data, downsample it, and then I have two ways to look at it. First, I can model the whole flow that I have, the whole Lorenz attractor, model the entire attractor, and then put the Poincaré section on the predicted flow. Or instead, I can use the Poincaré section, use the ordinal sections on the attractor, get the first return maps, and then model each of these first return maps separately. So, and I'm going to compare, okay, which of these approaches works better. So I have two sets as a reference, which, okay, I'm only using this one for as a data set, as a reference data set to model, but I know that if I had access to the high sampling rate one, that would be with that shape, and I'm using two modeling approach for doing so. Okay, first of all, I'm getting this one as a reference, and I'm predicting with my first approach, predicting the whole Lorenz first, and then put the ordinal coding on it. That's it. Here is the reference first return map that I have from the Lorenz. here is the first return map that I get from the predicted flow of the Lorenz, and this one is the comparison between the density of the points in these two diagrams. The blue, where the cell is blue, means that the density of the points in the reference one is higher than the predicted one, and when it's yellow, it means that in the predicted one, the density is higher than the reference one. I can see that the range of the color bar here decreased compared to each of them individually, which means that it wasn't too bad. They decreased the density, but it's not great as well. Yeah, that's it. And this is, if I with the second comparison measure that I defined, if I look at the radius of the circles, which contains the nearest neighbor points, from prediction set to the reference, and this one is from reference to prediction, the distribution of these radius is something like this, as long as I'm going through the time series. Here, this x values is from -7 to 7, something like that, which is this one, and for each point, I'm looking at the radius of the circle, which is. The second thing that I'm going to do is using the second approach, which means that, okay, I have this one, and I'm modeling all these points. Forget about the Lorenz time series, forgetting about the flow. I got these data and make the model out of it to get this one as my prediction, which is somehow awful. It's just filled all the empty values at the middle, and that's because of the modeling class that I use in radio basis functions. What I'm going to do is that, what I'm doing is that I'm choosing Gaussian function in somewhere and try to fit it to the data. So it will give me a continuous answer. It doesn't, I mean, it can't produce any discrete part shape for me. It makes it continuous because of the Gaussian function. And that's it. And of course, the radius of these circles also increase much higher compared to the previous situation that I have. And when I'm looking the radius of the circle from reference to the prediction, which is these middle points are the source, I have a high I have high value here for the radius of the nearest neighbor circle. If I want to compare the output of these two with the dissimilarity measure that I defined, of course, with the second approach, I can see that the range of the dissimilarity measure increased a lot. And also, with the first approach, which I predicted the whole flow and then put the Poincaré section on it, the dissimilarity from prediction to reference was always higher than the reference to the prediction. But with the second approach, they switched, and it's just because of the points, extra points that I have in the middle of my first return map. That's it. If I go to look at the Rössler as another example of time series, I'll do the same ordinal partitioning for Rössler, the high sampling one, the low sampling one. I see, okay, I have wider range for getting the points that are entering to this section, which are my first return maps point. But also there is another issue that Rössler is not all symmetric, similar to the Lorenz. And the effect of downsampling in different part of the attractor is different. So, for example, this one, which is on back of the attractor, when it's just twisting part, when I downsample it, it changes the topology of the first return map completely. It gives me another shape. They are not comparable anymore. But for this one, they are almost similar. These two are still okay. This one somehow these two are destroy the whole pattern. There are just some noisy bits, and that's a bit different and make it more difficult. But there is also another thing, that the first return map of the Rössler are not piecewise continuous like the Lorenz. If you look at the orange lines here, they are all in continuous, putting in a one shape, and that resolves the problem that I have with the extra points in the middle of the Lorenz first return maps. Here it is. Here is the low sampling rate one from reference, the high sampling rate reference, and the prediction that I made with the first approach, predicting the whole flow and then put the ordinal section on it. If I compare the densities, is like this. I can see that the range didn't change that much here, but it changed much better here. The range of the difference between the densities is lower. Here is the prediction that I made with my second approach, which is my prediction is much high there. It's not, if you compare it to this one, this is when I model the flow first and then put the ordinal section, and this is when I model the map directly and predicted it. And if I compare them, I can see that, okay, even without having access to the high sampling rate data at all, the modeling that I made from the map, the discrete map points, can somehow give me the shape of the high sampling rate versus the map, which I didn't use it at all as a reference data. It's just by using the RBFs, my model may give me access to the high sampling rate one, which can be cool. And if I put the dissimilarity measure to compare this one, again, okay, comparing any of my prediction with the high sampling rate one is much higher than the low sampling rate one, because even here, when I'm saying that, okay, I made a good prediction from high sampling rate version, there is a shift on the left-hand side of the first return map diagram, which because my measure is just looking at the radius of the circles, which contains the nearest neighbor, then here is a shift, which gives me large circles for the nearest neighbor, and that's not really a good thing in terms of my measure, but I can see that the shape is good. I like the shape. But okay, anyway, the value of this dissimilarity measure that I defined is high compared to the time that I'm comparing with low sampling rate one. And also, again, I have the switch here, which with the first approach, the dissimilarity from the reference to the prediction was higher, but for the second approach, it was lower, unless this one, which is the one that I showed you, that the topology of the first return map changed completely. It was just some random lines instead of a curve. And here, for this one, which I use I just modeled the maps by themselves as a discrete time series, and I predicted them. There is no special pattern between, for each individual first return map, the dissimilarity from reference to the prediction can be higher or lower compared to the vice versa. And that's the negative. The dissimilarity measure that I defined is not really strong in capturing the difference between the two sets, but there are some things happen here that's interesting. And if I just make a conclusion out of it, is can, okay, first of all, the ordinal first return maps that I define can be used as the measuring for sensitivity of the data for lack of data. That's for the Lorenz case, the first return maps didn't change that much, but for Rössler, in some part of the attractor, it's so sensitive to lack of data. And for the Lorenz one, which was the first return maps were piecewise continuous, the first modeling approach, which I'm predicting the flow first and then put the ordinal maps on it, it's better. And for the second one, the measure that I defined is not very helpful everywhere. It cannot capture so many similarities between the prediction and reference, and I can use better criterion for comparison. And that's it. Thank you.
Zahra, got any questions?
Can you go back to where you're comparing, just go back 2 or 3 slides. Yes, yeah, or measure of dissimilarity. Looking at the top right plot, why is it that you've got some ordinal patterns that have a real sort of difference between the reference and prediction distances, but then other points you are quite close, or like their distances are quite similar? Can you tell me what that might be?
Yeah, because I'm using, this is the reference that I'm making the model based on it. So it can change the topology of the real first return map completely. So when I'm making the model, it can lead me to this one, which is not similar to this one at all. So it doesn't necessarily mean that the modeling was not good. It was the effect of downsampling on that part of the attractor is very high.
But does that say anything about those specific patterns, or that they're the most sensitive?
I mean, you can look at each of them individually. It's not in a way that you can say a reason for all of them, because any of them can change the topology in any way, make them piecewise continuous, and if it's so comparing from the prediction one to the reference is similar to the Lorenz, that it's much higher. But I can't say a story that can cover all the sections.
Could you please go to the slide where you show that the RPF prerequisites of the Lorenz one, where the pictures don't look alike, and if this yellow point at places where there shouldn't be any.
I'm sorry, which slide?
The Lorenz one, the one where you said it wasn't very good.
Yeah.
Yeah, it's like
This one?
yeah.
Mm-hmm.
I'm just trying to understand. The densities are pretty low. When I'm seeing yellow points here and the white spaces, and we're seeing that as that's not good. Is that like, am I interpreting the yellow and the white as if there is a difference?
I'm sorry, I didn't understand your question.
So the densities are pretty low here, and we're saying
Okay. If the density is low, it's not exactly the thing that I care about. Is the thing that I concerning is that how much this range of the density of difference between these two is lower than the density of each of them individually. Here, the density of all the yellow points is exactly similar to this one because they are not canceling out anything from reference set. I mean, the perfect prediction is the one that I'm getting 0 everywhere, which can, all my prediction points cover the points that I had in my reference set.
I think Samson's asking how close is the yellow to 0?
Yeah, but if they are low, it's not the thing that I want to say, okay, my modeling was not as bad as that assume the major of the points of the yellow points are at the middle, which should be empty, and there is nothing here. The modeling can capture that, okay, these are the main points, and it put high density on these stuff, but still I have so many other extra stuff at the middle that I don't like them.
Yeah. Because usually when you try to, well I guess the question is how do we compare to distribution when we only have samples from it, right? Because the measures that we define here is pretty sensitive if you put the points in the middle.
Mm-hmm.
And point-wise differences actually might not be, you know, the measures that we want to sort of capture differences in distributions.
Yeah.
Yep.
Can I suggest a method number 3 for detecting distinction between sets of points? If you go back to when you explained the 5 nearest neighbour point picture. Yes, say go from this side to the other one, just looking forward. Yeah, so that'll do. So often the difference is because your red point is to one side of all the blue points. So your red point's about side the and in some ways that's worse than if the red points were surrounded by blue points. So instead of calculating the average distance or the distance to the fifth nearest point, you could treat those as vectors and add them up. So you've got five vector differences between red and blue, red and blue, red and blue, red and blue. Add them all together. They're all in the same direction. So you get a big vector, the big aperture. So it'll be bigger. But if the blue ones are all around the red one, they'll kind of cancel out. Very big things.
Yeah.
But if they're very big, some of them cancel exactly the size, right? So that's kind of just a little bit off. That minus that. Let's look at it.
These edge effects are suspicious. That's
Yeah.
and then the absolute percentage certain is actually it's artificial behavior. Essentially, but I thought you were going to say if you looked at that deep of it, how that changes with the subscriptors, so 3, 4, 5, 6, 7, 8, 9, 10. So then do the correlation.
There's correlation. So my suggestion is to basically borrow the order parameter that people use for synchronization. So the oscillator synchronizing. You know, when you try to measure how synchronized things are, you add them all up and you look at the phase.
Mm-hmm.
Aperture. Do the same thing here. If the phases are all over the place, then that gives you a measure closer to 0 if they're all on one side. So this would be synchronization. This would be bad because your red points an outlier to the blue points.
Mm-hmm.
Whereas Dave's saying calculate the correlation. But this is isn't it? How to go and do cross correlation? Wasn't that? There was. Yeah, that's what I said that.
I'm not getting 70.
Yeah, I've forgotten it, but yeah, it's a good idea.
Is there the one that fills in the piecewise? Is there any, like, just from a modelling perspective in general, like you need to be a bit knowing that it's piecewise in that way, should, like if you stuck with all top hats, for example, do you know that we get piecewise outputs, or does the description like not like bottom out until we've got so many top hats that we're filling space anyway?
Who you asking?
But in general, in terms of making anyone, we've all seen Michael's MDL now, so throw to the audience. But thinking about choosing the basis functions in some semi-intelligent way. Yeah. But I guess the objective with this sort of modelling is not being smart.
Then throw splines in.
Well,
So why is MDL selecting Gaussians over the top hats?
How spiky the top is. Because that cube parameter, Gaussian's in there. Cubes too.
Yeah.
And if you just got the evolution by 2, then
But wasn't the goal of the top hats to capture sharp transitions?
It depends on the queue.
yeah, the default is that Q is
Choose on random.
1 to 5,
Right.
which is so it's a negative x to the 5. It's quite dark. But I actually think it might just be the problem with the Gaussians is with the radius. They get big fat. So with the discontinuous one, so it's big fat shape opposed to flat. That's like a big. So both this nice smooth curve at the top. And using Gaussians, they're symmetric, so half is all wasted and getting up where it's no data. It's not penalizing for that. So it might be something to think what we could do better. Yeah, so if you think about that, yeah, the yellow points in the middle. So look at the top of that yellow point, that's pretty Gaussian. It goes up, it goes up. I mean, it goes up and goes down. So you can imagine fitting functions to both sides, and it's the 4 off as well. It's fitting both sides. Did you just try Gaussians and top hats? Basis functions first?
Yeah.
So not splines or cubics or cubes are the worst pretty fun.
Yeah.
Or sigmoids. Sigmoids might be. You can always write your own. All you have to do is write the function as derivative.
But so in theory, if your basis functions were discrete in this way, like not filling space,
But you can always use half Gaussians.
is that Gaussian? Is that splitting with the middle? Yeah.
If x is less than 0, 0. If x is bigger than 0, it's Gaussian. Not sure how you define possibilities. 2 dimensions. Yeah, 2. I mean, there's probably ways about it, ways to get this to work better. The real question is, how do they work that out? I mean, it's not really a question, it's not really an exercise in trying to best model. You get better models.
No, but like I'm just thinking in terms of if you've got something that's discrete,
Discontinuous.
discontinuous, yes, chunks. Sorry, I'm in my cellular automata frame of mind for next week's lecture. Should you be using functions that deal with that? Because potentially that's something that you know going into the challenge of modelling a process.
The other thing is you can replace the radial basis functions with neural networks. So it's a very easy switch to the code to replace x minus c1r with x dot c minus r. And then you've got, and the thing inside the bracket is equals rate minus bias, rather than input minus center divided by radius. And then you've got, because inputs minus weight, then you define a hypersurface, you define a direction for the basis function, where it can fall off. If it makes sense for either using hyperbolic tangent or just vector calculus.
Zahra, she was so showing us about sort of the function we're using. It was RBF and the motivation.
Yeah, so, but go back to the functions. Yeah, so but it's just linear, so in the linear and the constant part, that's fine, that's part of it. Because why use a non-linear model if the linear model is better? But what I'm saying is HT minus CI over rho, that's the bit that makes it radial. You just replace that with HT dot C minus rho. No norms in there. Then it becomes exactly the form of a neural network. Then you then fit in a single layer of neural network.
I distribution for the Gaussian.
Well, you can use Gaussian or you can use sigmoids or you can do whatever you want to use. Sigmoids make more sense because it's sigmoids are more traditional because that's what everyone uses. But it's also same to gradient this. According to stop using sigmoids, there's no reason to use them.
I thought it was easier to
Formal.
so
Possibly, yeah.
I think that is the reasoning that Luke's not putting these things on chips, so I think.
What did he have an alternative in mind?
Everything.
Right.
Don't be linked, don't be, but you could, so the point is that in that formulation, you define the basis function at a location with a radius. With h dot c minus rho, you define the basis function as something that changes in direction or volume to height. So you got the c defines the height, so the operation of the basis function goes up. It's a sigma. But you could have a top hat, this is something to take the other one to the first then can make half zero.
Instead of so.
is it talk about measurements?
So
Is it talk about measurements?
a top hat is a Gaussian that's either pointier, or if you take a Gaussian and you change the exponent, you either make it more square like a top hat, so the Gaussian, or it becomes more like a wizard's hat, or some variable. It's sort of this
Alright, do we have any other questions?
So can you tell us how you deal with the C's and the rows in the distribution?
Maybe it's been
Choosing randomly.
Right?
Choosing randomly.
No, you're asking about description info. Were you asking about how you deal with them in the description and calculation, or in the selection of them?
Are they not the same thing?
No. So you build a model, you choose your parameters, and Zahra's choosing the C's and the rows randomly. But if you want to calculate description and include the C's and the rows in that calculation, you need to calculate deltas for those C's and those rows, lambdas, but with respect to the C's and the rows. And then you differentiate in e to the negative norm of C squared with respect to C. So you've got a lot more terms in the negative. I'll give you a copy of my thesis.
Zahra, are you doing that? Or are you not doing that?
So right now the season
I think Samson knew the answer to this question.
it wasn't randomly, and the NDL part here was optimizing the D parameters.
Yeah.
I see.
Randomly with a specific method, or just scattered over space?
Randomly,
Inside the case, alright.
Better if you need to explain some substantial.
yeah, part 3 is subset. No problem. The simple answer is that you put the C's where the data is, where the error in the model is largest.
Yeah, okay.
And you choose the radius based on the spread out to the side.
Sure, sure.
Let's reduce the time. Just seems to
Well, it's randomly, but it's not. You choose your centers amongst random points. Or you build it, okay, so, you remember I was saying that you build the best NDL model size K, you go to K plus, you actually go from K to K plus 1. So you actually increase the model progressively. If you've got a model size K, essentially, but not quite, what you're doing is putting to one more basis function to that model. So what you do is you guess a whole bunch of possible basis functions, choose the best one. Now the way that you guess those basis functions is by guessing C's and rows. The way you choose the C's is you choose C's where the at data points where the error of the current model is largest. Okay. So because you've got a current model, if it comes to the basis functions, the current error of that model, no work performing badly. So each data point has got an error associated with it. And the probability of putting your center on that data point is proportional to the size of that error. So it's randomly, but with the probability that's the rows are just randomly. Some pattern. It's a whole lot of hand waving arguments that kind of works.
This is what happened in the fashion, where you view the model so far, and then the next one is based on what you had so far, but you the fact that if I had two more basis functions, things would be different.
That was the exactly, but not quite statement that I just made. So we choose one, but then we look at the moving one. So there's this. You have a k basis functions you wish to add one more, and now you try to remove one. The one that you choose to remove, based on as the lowest contribution to your error, the one you choose to remove is exactly the one you just added to the queue. If it's some other one, then you remove that and add something else. And so this, to get one, this gets around the two basis functions versus one basis function problem. So Samson's question is, if you're trying to fit, imagine a double arm function. Your best one basis function solution to that is a basis function that covers both points. Your best two basis function solution is two separate basis functions that cover each of them. But neither of those two functions are the one that you choose from this children. So you choose one, then you choose another, which will help you with one of the two functions. Then you throw out the one you started with and add a new one instead. And they have a basis function on each of them. That was my slide about Nakamura's mallet, because Tomo Nakamura's PhD was going up and down in and out, adding or removing basis functions to do all of this stuff in many different heuristic ways to figure out the fact that it's effectively a horrible nonlinear optimization problem. The solution we've got is good.
Alright, cool,
We
cool.
would do another PhD since.
Alright, let's thank Zahra one more time.
My apologies for being late, Zahra, but I was hoping the meeting notes would finish, but then someone said, what about this work placement stuff for PhD students? What can we do about that? And I said,